Are there any questions before we get started with this or back into this topic? So last time we were talking about WKB expansions for the Schrodinger equation, or an equation which we're going to call the Schrodinger equation. I actually was able to squeeze into one of the later sections, not in this slide deck, but in the next one, a discussion of the Schrodinger equation from the physics point of view. So if you've never seen the time-independent and the time-dependent Schrodinger equations derived from, actually, I don't go all the way back to deriving it from first principles, but we'll talk about it and derive the time independent from the time dependent Schrodinger equation. We talk about the classical harmonic, well, the quantum harmonic oscillator. I call it a classical problem because it's famous, not the classical harmonic oscillator is just a mass on a spring. The quantum harmonic oscillator is the probably one of the most important problems in quantum mechanics, at least the beginning stages of it. We're going to talk about that, and that ties in very well for us when we start talking about the subject of what are called turning points for Schrodinger type equations. But for the moment, it's enough for us to consider an ODE like this as our basic Schrodinger equation. And there are going to be two cases that we're going to consider up front. The cases, well, they can go under one sort of heading or one sort of main case, and that is Q is never allowed to be equal to 0. But this means we're going to consider the dichotomy where Q is going to be a positive function on its domain of interest or negative function, and in both cases bounded away from 0. We'll analyze those, or we did analyze those two cases separately. And then we're going to talk about the case of where Q could be equal to 0. That's called a turning point problem. So we derived the equations under these assumptions that at first Q was positive, and then we derived the asymptotic approximations in the case where Q was negative. When Q is positive, we're going to get an expansion which looks something like this. So this is our leading order WKB approximation for solutions of the Schrodinger equation. So to remind you, that Schrodinger equation had in it a highest order term, epsilon y double prime. I think it was minus q of x, y of x equals 0. So this, actually epsilon squared, this is a small parameter. So in this sense, it's a singular perturbation problem, but it's not, it doesn't give a singular perturbation, or it doesn't give the type of solutions that we examined in the matched asymptotics case in chapter 5. So the classical reason is because suppose that Q is negative, then let's say Q is just equal to a negative constant. In this case, the solutions to this problem are going to be sines and cosines. And as epsilon gets smaller and smaller, these start oscillating faster and faster. So remember, in the matched asymptotics case where we had boundary layers, we saw most of the time solutions which look something like that, where as epsilon was approaching 0, this was singular because we're going to lose one of the boundary conditions, but it was essentially converging to a function which is pretty well behaved. But in this case, we can converge to all manners of interesting solutions, one of which could be the case where the solution just becomes highly oscillatory. So that's the case whenever Q is a negative function and bounded away from 0. And we showed or argued that in this case, our WKB approximations were sines and cosines essentially. All right, then we did a couple of examples. This is just in a way of review since we missed last class. again, the solutions here don't look like the solutions that we encountered when we were talking about boundary layer phenomena. That's one of the important takeaways. We also showed that if you do go back to those problems that we encountered in chapter 5, namely this was the canonical linear problem that we examined there, where you do encounter boundary layers, we showed that the WKB approximation or expansion method can recover the basic solution ansatz or the basic solution framework that we got through matched asymptotic expansions. So in the boundary layer chapter, chapter 5, we showed that you have an outer solution, an inner solution where things are so we remember there was a very special structure of the solution. It had to decay as you move away from the boundary layer and back into the outer solution region. And so this type of solution exactly captures that. And then we have some sort of matching term, which we have to subtract off so we don't overcount. So I argued last time, we didn't get all the way through it. And I think because the details are kind of annoying, I don't want to go through this. All the details are in the lecture notes and in the slides. So the idea is the WKB method is this sort of global method, can recover the matched asymptotic solution without actually doing matching of an inner solution and outer solution and going through all that process. Furthermore, we're only looking at the lowest order, the leading order WKB approximation of this problem. If we go to higher orders, we can recover the higher order composite approximate solutions. So I'm not going to go through that in detail. We went through most of it last time. And so if you're interested, finish going through the details. At the end of the day, you can show that our matched asymptotic approximation or our WKB approximation is exactly the same approximation that you can recover with matched asymptotics. But it's a global method. It does this without ever considering matching terms and intermediate matching regions and things like this, intermediate variables. Kind of nice. Here's an example that we didn't get to last time and that I want to talk about this time. This is the model for what's called a slowly aging spring. So in this case, we have the following model, y double prime plus something here. If we would normally have a constant times y, this would be the model of a spring, where y would be the displacement from an equilibrium point. But here, the spring constant is not a constant. We'll call it a spring coefficient. It is some number which is decaying in time. Okay. Where epsilon is some small parameter, positive parameter. Let's pair that with the initial conditions that y at 0 is equal to 1. That's the initial position. And the initial velocity is equal to 0. I want to rescale this problem so that this term in the middle doesn't depend on epsilon. And to do that, I'm going to rescale time by introducing something called the slow time scale. Keeping in mind that epsilon is a small parameter. So if t is order 1, this tau has to be a very small time scale. We'll also introduce this new displacement function, y of tau, defined as y of tau over epsilon. You put everything back into the equation, substitute back in, and you get this equation. So this is a quote unquote Schrodinger type equation of or an equation of the type that we said we could solve with the WKB expansion method. So this is our Q function now. We have our small parameter epsilon squared, and the boundary conditions transform without changing at all, actually. Y of 0 is equal to 1, and capital Y prime of 0 is equal to 0. So this is the so-called slowly aging spring model or slowly aging spring problem. All right, so Q in this case is actually negative if you set things up in accordance with our framework. So it's equal to minus exponential minus tau. So as a negative solution, we expect our WKB approximations to be sines and cosines. And this is a typo here. There's no minus sign. Yeah, I hope I fixed that in the lecture notes, but if not, I will. I think I did. Just missed it here in the slides. So we know what Q is. What did I say Q was? It's minus e to the minus tau. If I take the square root of this function, square root of the absolute value of this function, I can integrate that exactly. So in the argument of the sine and cosine, I have to do this integral from a to t e to the minus s over 2 ds. No problem, I can integrate that. Now I'm allowed to choose a to be whatever I need it to be in this case. I could make this something like positive infinity so that when I do this integration, I get a 0. Or I can just leave it as a. That's going to be a constant, which I can absorb through changing these coefficients out front. So that's what I chose to do. I just let that as some a. You can say a could be set equal to 0, for example. It doesn't have to be a number such that the integral vanishes at that point of evaluation. So I can do all of this, these integrals exactly. The term out front becomes e to the t over 4. And so my solution looks something like this. My coefficients change a little bit because of this guy in the argument. So I'll call those new coefficients C tilde. So this is the approximation that the WKB method is giving me, and it's supposed to be valid for small values of epsilon. The constants are determined through using the initial conditions. We have 2 of those, right? So 2 initial conditions are y of 0 is 1, y prime of 0 is 0. And you can use those to determine these values. They turn out not to be all that pretty, but they're not terrible either. I just decided not to write them out. All right, so now this problem isn't so hard that you can't throw it on a computer and get a nice numerical solution. So that's what I did. I fired up Mathematica and did ND solve and gave it the initial conditions, and I solved it for a particular value of epsilon. And so when you do that, you get this numerical solution in orange, which appears here. And the approximate solution for using the WKB method, and here I'm chosen epsilon equals minus, or sorry, 0.05, not minus, but plus 0.05. You can see that the WKB method approximates this pretty much perfectly up until some very late or very large time t, or I guess this case it's tau equals 8. This approximation, or this curve here, is just the envelope of my WKB approximation, right? So that guy is just that function there. Otherwise, it's just an oscillator. Now, the period of oscillation does change, right? Because this is no longer a constant times t. So the period is changing, the amplitude is changing in some sort of complicated way. And by the way, so someone asked about method of multiple scales. You can use method of multiple scales to solve problems like this, where the period is a function of time, and also the amplitude is changing in some complicated way. All right, so there's WKB versus a numerical method, and quite a reasonably good approximation up until large values of t. And you can see that what's happening here is this is a pretty good or pretty interesting model of a spring whose constant is slowly weakening, right? So the thing starts oscillating larger and larger with larger and larger amplitude, and the period is becoming bigger as well as the spring constant weakens over time. Any questions?
So there's no forcing term for this spring system, but the amplitude is increasing.
No, there's no forcing. It's just that the spring constant is becoming weaker over time.
Oh.
Yeah. So yeah, so it's a little bit like you have the same spring, but it's becoming a weaker. It's like maybe like a rubber band whose elasticity is being lost over time. All right, now I want to talk about Sturm-Liouville problems. We're going to talk a lot about eigenvalue problems in this chapter, and that's because eigenvalue problems are really central to the theory of quantum mechanics. And this WKB method kind of lives in the field of quantum mechanics. It was born there, and it can be used to study eigenvalue problems with a lot of success. So I want to go back and review the concept of Sturm-Liouville problems, especially if you haven't seen them ever before or haven't seen them lately. So what's a Sturm-Liouville problem? Well, a Sturm-Liouville problem is an eigenvalue problem. You have some operator which acts on something, an object from a vector space, in this case, a function y. And we're looking for values lambda so that the operator, when it acts on certain functions y, just returns a lambda times that same function. So in the universe of matrix problems, we would write this as ax equals lambda x. So it's a similar sort of thing. In that case, the operator is a linear operator called a matrix. X is a vector in the usual sense that it has components from Rn, etc. But let's dig into this a little bit more. We're going to assume we have functions q, w, and p. Q and w are just continuous. P is a C1 function. W and P should be positive functions for all x in the domain of interest. Domain of interest here is a finite interval a to b. Now you can study Sturm-Liouville problems on infinite intervals. And in fact, when we meet the quantum harmonic oscillator problem, we're going to see a Sturm-Liouville problem, which is what we call a non-regular Sturm-Liouville problem. Regular simply means that these functions p, q, and w are fairly nice, and the problem is posed on a finite interval. This operator here, 1 over minus 1 over w, w is called the weight function, d dx, p of x, dy dx, plus q of x, y of x, is called a regular Sturm-Liouville operator. So the importance here is that it has some sort of what's called a divergence form for the highest, what's the right term? So the highest derivative term is in what's called a divergence form. In this case, it's a second order. You could study fourth order. It's not classical, but you could study fourth order Sturm-Liouville problems. The standard, of course, is second order. So the second order is in what we call a divergence form. And so this W is important. This one's called the weight function. We say that lambda in C is an eigenvalue of the regular Sturm-Liouville operator associated with the following boundary conditions. Now, when you talk about derivatives or differential operators, you always have to pair those with boundary conditions. Whereas operators of the sense or of the type that you encounter in linear algebra don't always have to be paired with boundary conditions. That doesn't make any sense. But in differential equations land or differential operator land, you always have to pair a differential operator with boundary conditions. The boundary conditions we have are so-called Robin boundary conditions of homogeneous type. Okay, so what is a Robin boundary condition? It's a boundary condition that involves a Dirichlet part and a Neumann part, or in other words, a point value evaluation of y and a derivative evaluation of y at the points A and B. Alpha 1 and beta 1 are associated to A, and this vector, if you want to think about it as a vector, this pair of numbers can't be the zero vector. In other words, you can't have both of these guys being equal to 0 simultaneously. You could have A1 equal to 0, that means B1 would have to be non-zero, and vice versa. So these two numbers cannot both be 0. That's what that is saying. And similarly with the boundary condition at point B, it's a Robin boundary condition of homogeneous type. So the homogeneous Robin boundary condition comes because we have this Robin piece equals to 0. Alpha 2, beta 2 also has to be such that those two numbers cannot simultaneously be 0. So we say that lambda is an eigenvalue of this operator with these boundary conditions if and only if there's a non-trivial function, that means a non-zero function. This is true for all eigenvectors. So whenever you look at eigenvectors, remember what the rule was. You're looking for values of lambda such that there's an associated eigenvector, which is non-trivial. It cannot be equal to the 0 vector. Same way, in Sturm-Liouville eigenvalue problems, we're looking for a non-trivial solution y, that means a non-zero solution y, that satisfies this equality with the boundary conditions 28 and 29. Let's see. We call y an eigenfunction associated to the eigenvalue lambda. And we refer to the pair lambda y as an eigenpair. So you're probably familiar with some very famous versions of this, like the fact that the sine function has a, well, I didn't come prepared to write an example, but let's think about one here really quickly. Suppose W is equal to 1, P is equal to 1, and Q is equal to 1. That's kind of the most famous version. Then we have minus y double prime. Actually, I want to set Q equals to 0. That's fine. So the problem that I'm going to solve is minus y double prime equals lambda y. And subject to the boundary conditions, y of A equals y of B equals 0. That's kind of the simplest version of these that you can solve. And of course, the solutions to this are just sines and cosines. In fact, you can figure out what the lambdas should be just by arguing that the boundary conditions should be satisfied in a certain way. And you can find then the lambdas are just going to be something like, well, it's related to pi, right? And the size of the interval that you're talking about here. So if I set, for example, A to be equal to 0 and B equals pi, then the eigenvalues should just be lambda is equal to k squared, right? Where k is a non-zero integer. I think that's right. You can check. But in any case, that's the classical Sturm-Liouville problem that has the sine and cosine eigenvalues, or sine and cosine eigenfunctions. So we're going to use WKB methods to approximate solutions to these eigenvalue problems in a certain situation. We can't always approximate them well with WKB methods, but we can in some cases. So here's a property of Sturm-Liouville problems. Suppose that y1 and y2 are given functions, and the Sturm-Liouville operator is defined as on the previous slide, with the same assumptions on P, Q, and W. Let's assume that the following boundary conditions hold. So in this case, we're just we're using the standard Robin, homogeneous Robin boundary conditions that I gave. In fact, these are the most generic versions of the boundary conditions that I could possibly give. The most standard ones, as I said, are maybe when I set this equal to 1 and this is 0, 1 and 0. So that's the homogeneous Dirichlet boundary conditions. In any case, we're still considering the very generic ones. Then the integral L of y1 against y2 integrated against the weight function w. Y2 has the complex conjugate, or you take the complex conjugate of that function, integrate from a to b, then you're going to find that you get the integral a to b of y1. Now you take the Sturm-Liouville operator and act on y2, take complex conjugate of that, multiply by the weight function, and you get the same integral. This can be represented in a nice, very simplified form if I introduce something called the weighted L2 inner product. So you might have seen this before. Weighted L2 inner product is just, with respect to this weight function w, is just defined as, for f and g functions, it's the integral from a to b, f times the complex conjugate of g against the weight function. The weight function is always assumed to be a positive real valued function, but the functions f and g are in general just complex of continuous functions on a, b with complex values. Okay, so do you all know how to take the complex conjugate of a function? So if f is a function from that function class, then it has a real part, which I can call h, and an imaginary part, which I can call g. And so the complex conjugate of that would be just the negative, okay? Or you just negate the imaginary part. So if I introduce this weighted L2 norm, then this condition up here can be written like this. All right. Now, this is probably familiar to those of you who have taken courses in linear algebra before. This says that the L operator is a Hermitian or self-adjoint linear operator in this weighted L2 norm. Okay, because I can take the L operator off of y, off of y1, and throw it onto y2. And the only sort of penalty that I incur by doing that is this is just going to be complex conjugated, which doesn't matter too much because in the definition of all this stuff, all of these functions that appear here, w, p, and q, are all real valued functions. Okay, so the complex conjugate doesn't really mess with those. It's only going to mess with the y function. Okay, so this just says that the Sturm-Liouville operator is a Hermitian operator. Okay. So the proof is actually much easier than it is to say. It's one of those. So I'm going to write this expression, the weighted L2 inner product of Ly1, y2. By definition, that's equal to the integral from a to b, the operator acting on y1 times the complex conjugate of y2 times the weight function integrated. So you can just substitute in what is the definition of this L function. Now, the L function is given with a minus sign and a 1 over w, and the w and the 1 over w cancel each other. So I just get this. Now, this, because it's written in divergence form, I can take this operator here, this single derivative operator from the y1 and throw it onto the y2, which is what I'm going to do. And the way I do this is to use integration by parts. Okay. If I do integration by parts, this derivative comes off of here, and then I just evaluate whatever's left at x equals a and x equals b. Then, of course, I have to throw the derivative inside the integral onto this y2 function. So I'm going to do that here. Am I doing it here? Let's see here. I did integration by parts twice. So I fooled myself. So what I did was I pulled this derivative off, threw it onto the y2. Then I had reattached p to that guy. And then I did another integration by parts. So that's why I'm getting exactly 2 boundary terms after doing 2 integration by parts. Okay, so I'm sorry if I confused you, but it's fairly straightforward. It's just a tedious little calculation. So 2 integration by parts, and that allows me to basically reassign the operator. Notice that this term here doesn't need any modification. It's only the derivative part. So basically, I'm taking the derivative part that was assigned to y1 and I'm reassigning it to y2 complex conjugate by 2 integration by parts. So if you believe that, which I think you should, all right, I'm not trying to sell you a bridge anywhere. If you believe that, then the next thing I want to argue is that this boundary term is just 0. And the reason the boundary term is 0 is because our homogeneous Robin boundary conditions will give us that. Now, it's not so obvious. If you know something about the Wronskian, so a Wronskian computation can show you that through those boundary conditions fairly easily. Otherwise, you have to go through some cases. Now, what I will say is it's fairly obvious that if I had these boundary conditions, the standard homogeneous Dirichlet boundary conditions, you can see it right away. Then these guys, for example, this term will be 0, this term is 0, and so the whole thing has to be equal to 0. It's not so easy to see that the homogeneous Robin boundary conditions guarantee the same thing, but it's a calculation that's doable. And so the boundary conditions fall away, and all I'm left with is this equals that. Now, P and Q and all that are real valued. So what I can do is I can argue that, well, this whole term that appears here is really just the complex conjugate of the whole operator applied to y2. And I've reintroduced 1 over w in the introduction of this operator L here. And so to compensate, because there's no w over here, I have to multiply by w. So that's why we're taking w to be strictly positive and bounded away from 0 on the interval of interest, okay? So now, then you just recognize this is the thing which appeared here. So the thing on the right, all of this jazz, is just this. And so that shows that L is indeed a self-adjoint or Hermitian operator. We say Hermitian in the case where we're using complex arithmetic. We say symmetric when we're using, did I say that right? Hermitian when you're using complex arithmetic, and symmetric when we're using real arithmetic. Or in other words, the field over which we're pulling these functions is complex versus real. Okay, so the L operator is Hermitian. Well, what do we know about Hermitian operators? Anybody remember? What do you know about Hermitian operators? What do we know about the eigenvalues right away?
The positive definitely.
No, not quite.
They're real.
They're real. So we immediately know that they're real. And then we can use some arguments, maybe some extra assumptions to argue that the eigenvalues have to be maybe positive or they could be non-negative. Maybe a zero eigenvalue is possible. And otherwise, all that we can say is that they tend to be, or you can show that they are bounded below. There's a smallest one. There's a smallest eigenvalue that is real. But is there a largest eigenvalue? So in the theory of Sturm-Liouville operators, it turns out there's always the smallest. All the eigenvalues are real, but there's no largest eigenvalue, which is a kind of curious fact, right? But we'll see that it's not so curious. Suppose that lambda is an eigenvalue of the Sturm-Liouville operator subject to the boundary conditions, the homogeneous Robin boundary conditions. Then lambda actually is real. Lambda has to be a real number. If we additionally assume that Q is greater than or equal to 0, and this boundary data or this boundary condition holds, or this boundary information holds, minus P of X, Y prime of X, complex conjugate Y of X, evaluated at X equals A, X equals B, difference is greater than 0, then it follows that the lambdas are all greater than or equal to 0. If I say very simply, if I use the homogeneous Dirichlet boundary conditions, then we can show that the eigenvalues have to be positive. They simply have to be positive. All right, let's see how to prove this. Since lambda is an eigenvalue, there has to be a corresponding non-trivial function y associated to it. So y being non-trivial means that it's not equal to the 0 function. So L of y has to be equal to lambda y. They're a pair. They go together like peanut butter and jelly. Y satisfies boundary conditions 28 and 29. And since y is non-trivial, what do we know if we put y into this inner product? What do we know that's going to happen when we evaluate this inner product? Well, if y is non-trivial, w is also a non-trivial positive function. So this whole thing integrated is non-negative, right? But actually it has to be essentially, there has to be a place where has some essential mass. So this integral has to be positive.
I mean, W is not 0.
That was our assumption, because otherwise you get into the theory of non-regular Sturm-Liouville operators. So we're assuming, I might have forgotten to say this, I'll have to go back if I didn't. So you assume that it's bigger than some W naught, which is positive, bounded well away from 0.
I think because if your Y is non-zero somewhere, but actually W is non-zero elsewhere.
Right. Yeah, let's see if I remember to say that. Let's see. So this, okay, so they're continuous functions, right?
Yeah.
And they're bounded away from 0, right? So that means that the minimum has to be bounded away from 0, right? So that I don't have to add that assumption. This is already there, right? Does everyone get that? Because it's a continuous function on a closed compact interval. So this guy is bounded below, well away from 0. This has to be a positive integral. Okay, so let's go through this calculation. Take lambda times that inner product of y with itself in the weighted L2 inner product. So now what we know about this inner product here is that it's what we call conjugate symmetric. So if I have a lambda outside, I can reattach it to the first argument without a complex conjugate. If I do that, well, that's lambda y, so that means that this is L times y. But we know that L is a Hermitian operator, so L can hop from here over to here. It just hops over, right? Now we get Y lambda there, correct? But remember, this gets complex conjugated. So that's where the conjugate symmetry aspect comes in. So lambda, when it comes back out from this second location, comes back out with a complex conjugate. Okay? That's because of the fact that my second argument in my weighted L2 inner product is conjugated. So it comes out with a complex conjugate, but now we're allowed to cancel this and that. We can simply divide, right? But you see lambda has to be equal to lambda bar, complex conjugate. The only way that that can happen is if you have a real number. Does that make sense? All right, now, since lambda is an eigenvalue, it's equal to its corresponding Rayleigh quotient. And that follows simply from this calculation up above. So somewhere in here, we can use this guy here and divide by that. So lambda is just equal to that. So you can see that's part of this computation. Very simple. That's called the Rayleigh quotient. This object here is called a Rayleigh quotient. So what? Well, let's check it out. So the result then that we want to show, that is that the eigenvalues are greater than or equal to 0, is going to follow if this whole thing is non-negative. Or if I could show that this is positive, then this shows that every lambda is positive, right? And this is the style that you use to prove that. So the bottom is definitely positive because y is non-zero, so we're dividing by something non-zero. So all that matters here is the top. If we can show that the top is greater than or equal to 0, then that shows that the Rayleigh quotient is greater than or equal to 0, shows that the lambdas, the eigenvalues, are also. So let's just play around with this. So take the operator act on y. That's just exactly equal to this. Ly integrated against y complex conjugate integrated against the weight function w. When I introduce what this is by its definition, it has a 1 over w. That cancels with w. Now I can integrate by parts. And now when I do integration by parts, I'm just going to do it once, I think. Yeah, just do it once. So you get this term when you do one integration by parts. And you're left with this integral here after pulling off that derivative from this divergence form of the operator. And so I get P times this, Q times this. So our assumption was that Q is non-negative. P is always positive by assumption. This whole term can be written as P of X times the absolute value of dy dx squared. Actually, this means modulus. I should say not absolute value, but modulus. Do you remember what modulus means? So if I have a complex number, z equals x plus iy, then the complex conjugate is x minus iy. And the modulus of z is defined as x squared plus y squared, square root. Another way of saying the modulus, modulus squared, is z times z bar. Okay. So in any case, this number here is now non-negative. This number is non-negative. By assumption, this is non-negative. So every term in sight is non-negative. When I integrate a non-negative function, that's non-negative. So the whole thing has to be non-negative, greater than or equal to 0, right? So that shows that this numerator is non-negative. The bottom is positive, so that means that lambda has to be non-negative. And of course, you can contrive situations where this is strictly positive. You can assume that Q is strictly positive. Since P is also strictly positive, then you can derive necessary or sufficient conditions for the eigenvalues to be positive. Okay. Now, in general, you can show that even if this is not greater than or equal to 0, I can show that my Rayleigh quotient has a minimum. Okay, a minimum. So that tells me that I have a smallest eigenvalue. Not necessarily a largest eigenvalue, but at least I have a smallest eigenvalue. That's the technique that I would use. In any case, let's move on. Suppose that lambda 1 and 2 are distinct eigenvalues of the of the Sturm-Liouville operator subject to the homogeneous Robin boundary conditions. Let's assume that y1 and y2 are associated eigenfunctions. Then, if these really are discrete real eigenvalues, remember all the eigenvalues are real, then the inner product of y1 against y2 is just 0. In other words, y1 and y2 are orthogonal in this weighted L2 norm. Does everyone know what orthogonal means? Okay, so this is an abstract statement of orthogonality. You may have heard of orthogonal polynomials and orthogonal functions. If you're a physicist, then these are very important. When you talk about the Hermite polynomials in the context of the quantum harmonic oscillator, that's a system of orthogonal polynomials, as are the Lejeune polynomials and the Laguerre polynomials, etc. Lots and lots of really neat functions which satisfy orthogonality or orthonormality relations with respect to some weighted inner product. How do we prove this? How do we prove this orthogonality? Again, we're going to use the fact that L is Hermitian and lambda I are real to do this. So let's start off with lambda 1 times y1 inner product with y2 in this weighted L2 inner product. So I can move the y1 in onto the the lambda 1 onto the y1. So that means that can be replaced with L of y1. L is a Hermitian operator, so it can hop from y1 over to y2. Once it hops over to y2, then it's going to spring forth this lambda 2, the eigenvalue associated to y2. When that lambda 2 comes out of the inner product, it comes out with a complex conjugate, because remember, this inner product is not symmetric, it's conjugate symmetric. But remember, lambda 2 is real, and since lambda 2 is real, the complex conjugate falls away. But now take a look at this and that. So notice that this is just a number, and this is the same number. Lambda 1 and lambda 2 are distinct eigenvalues. So that means if I subtract one from the other, I don't get 0. So let's take this guy and move it to the other side. Subtract, use cancellation property, right? Additive cancellation. What do you get? Lambda 1 minus lambda 2 times the number y1 against y2 inner product. Well, that has to be equal to 0. But lambda 1 and lambda 2 are certainly not equal, so this difference can't be 0. So the only way that this can hold is if this inner product is equal to 0, and that's the proof. Lambda or y1 and y2 must be mutually orthogonal. Does everyone understand that?
So in the matrix case, we sometimes need to do orthogonalization. So in this case, we don't even need to do that.
So even in the matrix case, you get orthogonality for free. But normality is you may have to normalize, but you get the orthogonality for free. So if I have a symmetric or a Hermitian matrix, I know that my eigenvalues are real, right? So eigenvectors associated to distinct real eigenvalues of a Hermitian matrix have to be, did I say that right? Eigenvectors.
But in the matrix case, if you have the same eigenvector, as two eigenvector corresponding to the same eigenvalue, they may not be orthogonal. They can be
Right.
they're only independent. You need to do
Yeah, I mean, they might not even be independent. You have to have a big enough eigenspace so that they could be independent, right?
So it's eigenvector in this sense unique. Like if I give you one eigenvalue.
Yeah, so the eigenfunctions here are unique up to multiplicative constant. Yeah. Yeah, that's true because essentially my eigenspaces are all one dimensional.
Is there any easy way to see?
Not that I know of. Let's see. I think it's a little bit non-trivial. When I go to 2 dimensions, then of course your eigenspaces can be 2-dimensional or higher dimensional. And 1 dimension, I'd have to think about a simple proof. Maybe there isn't one. Yeah, that's a good question. How do you show that the eigenspace for each eigenvalue is only 1-dimensional? That's a good question. I don't know off the top of my head. It is true though, in 1 dimension for these regular Sturm-Liouville problems, it is true. And let me know if you find that proof by the end of the lecture. So here is a summary. I think this is the summary result for Sturm-Liouville problems, which has some results in here that I proved and some results which I'm not going to even attempt to prove because it's a bit too complicated. All right, so we're considering the Sturm-Liouville operator that we introduced earlier in the definition. That's 27, with the homogeneous Robin boundary conditions 28 and 29. The eigenvalues are real and they're countable. There's the smallest eigenvalue, and you can show that because you can show that the Rayleigh quotient always has a minimum, has a bottom. But there is no largest eigenvalue. And if the eigenvalues are ordered in the following way, you just stack them, the lambda 1 being the smallest, lambda 2 being the next smallest, and so on. Then the limit as k goes to infinity of lambda k is infinity. In other words, the largest eigenvalue is, well, there is no largest. Or you could say the largest eigenvalue is in some sense infinity. It's not hard to see this through that canonical example, sines and cosines, whenever you have the problem that I mentioned earlier, the eigenvalues were k squared. And so as k goes to infinity, k squared goes to infinity. There's no upper limit on that. For each eigenvalue lambda k, there exists a corresponding eigenfunction yk, which is unique up to a multiplicative constant. This essentially addresses the case that Calvin mentioned. There really is a unique eigenfunction up to a multiplicative constant. That means the eigenspace for every eigenvalue is 1-dimensional. There's only one. There's really only one object in there. Here's another interesting fact. This is cool as heck. So yk is unique up to a multiplicative constant and has k minus 1 zeros in the interval a to b. Okay, so you can see this with sines and cosines as well. So in that canonical example, the eigenfunctions are the sine function, right? So it's sine, what is it, k pi x, right? And if I look at sine k pi x, so the first one looks like that. No zeros, right? The second one looks like that. So it has exactly 1 0 in the interval. The third eigenfunction looks like that, 2 zeros, and so on. This holds all the time. This always is true. Okay. A very amazing property. What else? Eigenfunctions corresponding to distinct eigenvalues or orthogonal with respect to the weighted inner product. We did prove that one. The set of eigenfunctions which can be normalized. Normalization just means that whenever you decide on your inner product, you normalize by saying that when I integrate or whenever I take y1 or yi in both locations, yi, then I just get a 1, okay, for all I. Oh, a succinct way of saying that is just to say that yi against yj in the weighted inner product is the Kronecker delta symbol. Kronecker delta ij means it's the symbol which is equal to 1 whenever I and j are equal to each other, and it's 0 otherwise. That's the Kronecker delta. And this system is complete in the following sense. If I have any function f in this weighted L2 space, then it's equal to or can be expressed by its Fourier series. Okay, this is what I would call a generalized Fourier series. So these coefficients here are called Fourier coefficients. But if you know how to do regular Fourier series, getting these coefficients is more or less the same. Here, I guess I didn't need to divide by that. That's just equal to 1. I forgot my normalization.
The first part is just Gram-Schmidt.
Gram-Schmidt. I don't need even Gram-Schmidt because I know that the eigenspaces are one-dimensional.
Oh, yeah, they must be the whole.
And I have them orthogonal, so that already is done. What I need to show is that they're complete, right? That that any function in this space can be expanded in its Fourier series.
I also found which
Okay.
is sleep. So L of y equals to lambda y is the second order ODE with two normal conditions, so it must be unique.
Oh, okay. Oh, it's by uniqueness. Okay. Once you fix lambda, then okay. Yeah, it is sleepy. That's good though. I'm glad you found that. All right, so where would you find a proof for this? I've listed here a reference, but you can find this in a lot of good books. So it goes under the Sturm-Liouville theory. And notice I haven't touched the irregular Sturm-Liouville problems, only the regular Sturm-Liouville problems where our domain of integration or domain of interest is a finite interval. And also my weight functions cannot decay down to 0. They have to be bounded well away from 0. If you look at the cases where these weight functions can decay, then this gets you into the realm of what's called irregular Sturm-Liouville problems. For example, if you ever heard of, we've discussed it here before, Bessel's functions and Bessel's differential equation, and the other one of interest is the Hermite differential equation, which has the Hermite polynomials as solutions. Then these are examples where the weight functions degenerate down to 0. The Bessel functions are probably the most famous of the degenerate problems. Okay, now I want to talk about an eigenvalue problem of the type that we're going to kind of screw around with here within the context of the WKB method. So let's consider the following linear ordinary differential equation. And I've normalized this, or not normalized, but I've just decided to make the interval of interest 0 to pi. E here is some real number, and I'm looking for solutions that satisfy this differential equation with these boundary conditions, these homogeneous Dirichlet boundary conditions. So this is an eigenvalue problem because I'm not going to specify what E is, I'm going to calculate what E is. So I'm asking what pairs satisfy this equation, E and Y, where Y has to be non-trivial. So here we're using E for eigenvalue because this is the most standard notation in the quantum mechanics literature, where here E is going to stand for energy level. So this is a Sturm-Liouville problem. And you can see that it fits a canonical form. It's the Sturm-Liouville problem, which is given to us by setting p equals 1 and q equals 0. So in this case, we know that there are an infinite number of eigenvalues, E1, it's indexed by k equals 1 to infinity, and there's a smallest one. It turns out that smallest one is actually positive. Now, I guess this should say, I think I have a typo here. That should be W, right? Right, so that should be W. Whatever the heck W is, we're just going to assume that it is a continuous function, that it's everywhere positive, so that it fits the regular Sturm-Liouville theory that we outlined above.
You type Q probably because you're thinking about a household job here.
No, I typed Q because I originally had a Q there, to be honest. All right, so now we can approximate the solutions to this equation if we think about E being a large number. Because think about it, if E is large, I can throw E over to here, just divide through by E, and a large E now becomes 1 over a large number when I write it here. That's the small number, right? And so that's precisely the framework where I can apply WKB theory. Because remember, WKB is epsilon squared y double prime plus W of x, y of x equals 0. Okay, what makes this the question is, what makes this an eigenvalue problem? Well, there are kind of two things that make this an eigenvalue problem. Number one, this is homogeneous over here. There's a 0 there. And I have homogeneous boundary conditions. So those two features, well, and the fact that this fits the Sturm-Liouville operator framework after doing a slight cosmetic fix-up. And the slight cosmetic fix-up is you move this guy to the other side, multiply through by a minus, okay? But it can all be put in order. But really what makes this a Sturm-Liouville problem, an eigenvalue problem, is I have homogeneous information there and homogeneous information here, okay? And it fits. So now, just because this is an eigenvalue problem doesn't mean that we can't bring to bear WKB theory on it. It just means that when we apply WKB methodology, what we're approximating whenever we do have a solution is the eigenvalues and eigenvectors. So let's see how this works. So here's our WKB approximation. Remember, I have to replace 1 over epsilons with a square root of E because they're the same thing, right? So more or less, I have 1 over E is equal to epsilon squared. So 1 over epsilons would be just square root of E, right? So otherwise, because of the sign on W, the approximation that I need to make, or the one I need to use, is associated with the Q being negative. And that's sines and cosine solutions. Q negative, sines and cosine solutions. I'm going to use A and B for my unknown coefficients here rather than tilde C, blah, blah, blah. All right, but now this we can just state is our approximate solution. So let's operate on it as if it is. So we have this as our approximate solution. Let's apply the two boundary conditions and see what happens. If I put in y of 0 equals 0, then immediately I see that the cosine is going to be cosine of 0, which is just 1. And sine, if I put in 0 here, this is just going to be 0, so this whole term goes away. But the boundary condition says y of 0 is equal to 0, so that tells me that a has to be 0. So I immediately lose that term, and I only get sines. That's nice because that corresponds to our canonical case where we had sines, our canonical or simplest eigenvalue problem where the solutions were sines. Otherwise, they're not sines. I mean, you know, depending on what W is, it's something sine of some complicated function. The second boundary condition is what quantizes the eigenvalues. So in quantum mechanics, everything is about quantizing this and quantizing that. And really, I think the early quantum mechanics people thought of everything as being quantized, but really mathematicians understood this as just eigenvalue and discrete, you know, eigenvalue problems from the very beginning. But in the quantum context, it's quantization. So this second boundary condition is what gives you the quantization. Because the second boundary condition is only satisfied if this whole thing is equal to 0 at, what was it? X equals pi. So if I put in x equals pi, then this argument here becomes square root of e, integral 0 to pi, of square root of wt dt. Well, that has to be equal to pi k. That has to be equal to pi k, where k is an integer. Why? Because this whole term has to be a multiple of pi in order for that to be generically 0. So that's what determines our eigenvalues for us. Or in other words, that's what quantizes the energy. Now, how do I know that this is a positive value of k? Well, this energy I'm assuming is going to be a positive number. Otherwise, this is going to be like a complex number, right? Well, I know that these numbers can't be complex in the first place, so this must be a positive number. E has to be positive. What do I know about this guy? W is a positive function. Square root is a positive function. I integrate that, I get something positive. So this whole thing here has to be positive. So that's why I choose pi k, where k is a natural number. Otherwise, I could say it could be any integer, right? But it has to be the positive integers. So now I can just solve for these quantized values of the energy. And if I do that, I just get this. So this tells me how to approximate eigenvalues using the WKB method, where all I'm assuming is that k is large. K is large corresponds to the fact that EK is large, and that should be the regime where I can use these WKB approximations. Does everyone get that? You can also approximate the eigenfunctions themselves, not just the eigenvalues, but the eigenfunctions. Once I have this quantization figured out for EK, I then know what my eigenfunctions are. Now, the BKs, how can I determine those? I can determine those through the process of normalization. Now, you don't have to normalize in this inner product, but that's a pretty standard process. Normalization just means that when I integrate 0 to pi, yk modulus squared against w is just going to be equal to 1. Okay, so now I might not take that exactly equal to 1, but as long as it's asymptotic to 1 as k gets large, then I'm happy. So this tells me that this tells me what I need to have for my value of my b function, or my coefficients b. So if I work this out, then bk comes out to be exactly this. So this tells me exactly, well, kind of exactly what my approximation should be for my eigenvalues and eigenfunctions. So let's try this out on an example. Remember, this should only be appropriate for large values of the eigenvalues. In other words, for K being very large. And for K being moderately small, this approximation shouldn't be all that great. But it turns out it's pretty good. It's well, in some cases it's exact. So for our canonical eigenvalue problem, that's where the weight function W is exactly equal to 1. So our WKB method predicts that the eigenvalues for K large are going to be K squared, but those are the exact eigenvalues. And it says that our eigenfunction should be square root of 2 over pi times sine kx. That turns out to be exact as well. So the WKB approximation is exact whenever W is exactly equal to 1. But that's not a truly realistic example. So let's suppose that W is equal to this function, something a bit more non-trivial. With these boundary conditions, should be a space between there. Then our method predicts that the eigenvalues are asymptotic to 9k squared over 49 pi to the 4th as k gets large. Remember, our approximation should only work as k gets large. And we approximate our eigenfunctions as this bad boy right here. So Mathematica is, I couldn't get it to work in the slides for some reason, my Mathematica code, but trust me, there's a very simple code for approximating eigenvalues up to any number that you want using Mathematica. It's a very slick little command. So I did that. I computed, actually you can compute the eigenvalues and the eigenfunctions in Mathematica. So here's the true eigenvalues compared to the WKB eigenvalues, even for very small values of K. And you notice that if I compute the relative error, that for the 5th one, I'm getting a pretty small relative error already. So these are true eigenvalues in the sense that they're computed numerically to hopefully some nice precision. And here are the eigenfunctions. So this is whenever K is equal to 2. That's not very large, folks. That's pretty small, right? So K equals 2. Our WKB is in blue, and in orange is the exact eigenfunction. And I had to take the eigenfunction computed by Mathematica and normalize it properly. So I did the normalization, I guess you could call it renormalization because they use some other normalization. And when I did that, they pretty much overlapped. And whenever K is equal to 3, we get this approximation in blue. The blue is pretty much hidden underneath the orange curve, so it's doing pretty well again. And so notice that it's following the pattern that we mentioned before. It has exactly 2 zeros in the interval 0 to pi. That's pretty cool. So again, this is not very large. K equals 2, K equals 3. We're already getting really good approximations using the WKB method. So remember I said this chapter, we're not doing too much rigor. We're doing mostly proof by comparison. And so already I'm pretty pleased, pretty impressed. So next time we talk about what are called turning points. So far we've considered Q, where Q is bounded away from 0, either positive or negative. Next time we're going to examine the case where Q could be or have regions where it's positive and negative, and it has a crossing point where Q is equal to 0. This place where Q is equal to 0 is exactly called a turning point. And it's called a turning point for the applications that arise in quantum mechanics and even classical mechanics. So we'll talk about that next time. I have, so there's 2 slide decks for chapter 6. So we're almost through the first one. And then I have one more. So forecasting, going ahead a little bit, we're going to talk about 1 turning point problems, and we'll talk a little bit about quantum mechanics. So if you've never seen that and are interested in that, I encourage you to tune in for that. And then we're going to talk about turning point problems where you have multiple turning points. So that's what's coming. I will see you guys on Thursday. Have a nice day.